So today we're going to go through how to sketch and do calculations for mirror problems. You're going to be needing to do something like this on the test for this module. So make sure that you bring a straight edge and are able to do these drawings. So how do we draw a mirror problem? Well, first of all, draw the mirror, draw the principal axis, which is the horizontal line going through the mirror, draw the focal point and the center of curvature. Then draw your object on as an upright arrow and make the tail of the arrow on top of the principal axis and make the distance from the mirror approximately correct given what the center of curvature and the focal length are. Draw the three special rays. Remember, the incoming ray must pass through the arrowhead, and the head of the image arrow should be located where the three reflected rays meet with its tail on the principal axis. And the three special rays are one that comes in parallel to the axis and reflects through F, or for convex it extrapolates out through F. A ray that comes in through F and reflects parallel to the axis, or a ray that comes in through the center of curvature and reflects back on itself. So let's go through a bunch of examples. So we're going to go through basically all the different possible situations there could be. All right, so for this one, we're going to start off. This is, what is it? It's a concave mirror because it's shaped like a cave. The light's coming in from the left side. So we've drawn the mirror. We've drawn the principal axis, which is the horizontal line. We've drawn the focal length and the center of curvature, which is twice as far out as the focal length. And so here we have an image, so an object O that's outside of F but inside of C. So the first thing we have to do is draw these three special rays, and then we want to figure out how would we describe the image. So ray 1 comes in parallel to the axis and then reflects out through the focal point. So what you're going to do is you're going to take your straight edge and you're going to start at the object, the tip of the object, and you're going to draw a line straight across until it hits the mirror. So you can go like that. And then that ray is going to bounce back from the point where it hit the mirror. So you're going to start off with the arrowhead there and go through the focal point. So you're going to put your ruler, your straight edge, so it goes between those 2 points, and you're going to draw a line that goes down. So that's my special ray 1 in red. Okay, special ray 2 comes in through F. So when it says comes in through, that means that it has to go through the tip of the arrowhead and it has to go through F. So you're going to put your straight edge on the tip of the arrowhead and on F, and you're going to draw a line that comes in till it hits the mirror, and then it's going to turn and go back out parallel to the axis. So the green horizontal line going out is my ray 2. Okay, what's ray 3? Ray 3 says it comes in through the center of curvature and reflects on itself. So what we do for that one is we just put our ruler through the tip of the object arrow and on the center of curvature, and then just draw a continuous straight line, hits the mirror and bounces back on itself. So sort of like that. All right, so now where is my image? Well, my image is at the point where those three reflected rays meet, so it's going to be at the point over there below the line near the left. And so we're going to draw our image arrow there. It's a good idea to label it as the image. I put the tail of the arrowhead on the line, and the tip is where the rays meet. So how would I describe that image? Well, it's upside down, so I would say inverted. Is it real or virtual? Well, it's real if the light that's reflected really goes through it, and it does. So it's real. Does it look like it's smaller or larger? It looks like it's larger than the object. So it's inverted, real, and larger. Okay, let's do another one for a concave mirror. So concave mirror, draw our horizontal line, principal axis, put on F and C. Now I've got my object is closer to the mirror than the focal point. All right, so now we draw our three rays. So it comes in parallel to the axis. So we draw a line parallel to that principal axis, and it's going to pass through the tip of the arrow, and it's going to continue until it hits the mirror, and then it's going to turn around. It's going to reflect through the focal point. So we're going to put our straight edge from the point where that ray hit the mirror and F, and make a line that goes straight down through there. All right, ray 2 comes in through F. So what does that mean? That means as the ray's coming in, it passes through the tip of the arrow and through F. So I'm going to draw a line like that goes through the focal point and through the tip of the arrow. And you'll see this time this ray goes upwards instead of downwards because the object is inside the focal length. And then it reflects back parallel to the axis. So we draw our green line going out like that. All right, ray 3 comes in through C and reflects on itself. So what do? We put our straight edge on C and on the tip of the arrow and just draw a long straight line. All right, so now the question is, where do we put our image? Well, we put our image where the rays meet. But if I put my eyeball over here and I trace that green arrow coming back, the red arrow, and the blue arrow, you can see those rays are spreading apart. So what do? Well, what I do is I extrapolate those outgoing rays backwards. So you can see I put in some dashed lines there. And you can see that those rays look like they're coming from a point that's behind the mirror. So the point where the tip of my image arrow is going to be is where those 3 dashed lines meet. The tail of the image arrow is going to be on the principal axis. So there's my image. So now how would I describe this image? Well, it's upside right, so we say it's upright. Is it real or virtual? Well, we had to draw imaginary lines to go back behind the mirror, right? Light doesn't really go behind the mirror, so the fact that we see a virtual image behind the mirror, the fact that we see the image behind the mirror means that it's virtual. I gave you the answer. So it's upright and it's virtual. Is it smaller or is it larger? Well, it looks like it's bigger than the object, so it's upright, virtual, and larger. All right, let's quickly go through some more examples. What if I move the object outside the center of curvature? So now same thing. So first ray comes in parallel to the axis. So I draw a line that passes through the tip of the arrow and is parallel to the axis, hits the mirror, then it turns around and it bounces out through F. So again, you're going to take your straight edge, you're going to put it at the point where the ray hits the mirror, you're going to put it at the focal point and draw an arrow going back out. Okay, ray 2 comes in through F and reflects parallel to the axis. So in through F means you put your straight edge on the tip of the arrowhead, you put it on F and you draw a line that goes in and hits the mirror. And now it bounces back from that point parallel to the axis. All right, ray 3 comes in through C, so that means your ruler goes on the center of curvature and it goes on the tip of the arrowhead. Draw the line like that. Okay, so where do these rays meet? Well, if I look, the reflected rays all seem to be meeting at that point there. So there's my image. So my image goes up to the axis and down to those points. So it's upside down, so it's inverted. Is it real or virtual? Well, it's in front of the mirror. The light rays are really hitting it, so it's real. And it looks like it is smaller. So it's inverted, real, and smaller. All right, last example. This is for a convex mirror. So for a convex mirror, the focal point and the center of curvature. Remember, the center of curvature is where you would put like your compass from your geometry set if you were going to trace out and complete this circle. Okay, so it's a point that's right at the center of the circle if I were to complete it. So those are virtual focal point and virtual center of curvature because they're behind the mirror. And it turns out that we always have the same situation no matter where we put the object in front of a convex mirror. All right, so let's draw it. So ray 1 comes in parallel to the axis till it hits the mirror. So that's easy. And then it reflects, or we say that it extrapolates, the reflection extrapolates through F. So what I do is I draw a line that bounces back from the mirror such that its extension goes down and hits the F on the other side. So usually what I do is I put my straight edge at the point where the first ray, incoming ray, hits the mirror. I put it at F, and then I draw my solid straight line on the same side of the mirror as the object, and then I draw a dashed line going back through the focal point, and the dashed line just indicates that that's a virtual ray. It's not really there. All right, then ray 2 comes in through F. So if it comes in through F, I'm going to take my straight edge, and I'm going to draw a line that goes from the tip of the arrow to F, and then I'm going to draw that line, and I'm going to draw the line as solid until it hits the mirror, and then dashed afterwards. Okay, once it hits the mirror, it reflects back parallel to the axis, so I can just draw it like that. All right, last one is a ray that comes in through or extrapolates through the center of curvature. So now you take your straight edge, you put one end on the arrowhead, one end on C, and you draw a long straight line that extrapolates through C. So now if I want to know where is the image, so again, I put my eye over here and I look at my reflected rays, which are this one, and this one up here, and you can see they're spreading apart. So what I have to do is I have to extrapolate those reflected rays back. So the red extrapolation that's already there, if I extrapolate the green reflected ray back, that's just a parallel to the axis, the blue one back, and then you can see that the three rays meet behind the mirror. So I get an image that's virtual and upright. And when it's virtual, it's always upright. When it's real, it's always upside down if you have a single mirror. So it's inverted. So it's upright, it's virtual, and it's smaller. And this is always the case. So whenever you have a convex mirror, you will always get an upright, virtual, smaller image. Okay, so what if we want to do a calculation? What if we can't tell from our picture whether it's bigger or smaller? Well, we can use equations to calculate it. So we can calculate the object distance, image distance, and F related to each other by 1 over dO plus 1 over dI equals 1 over F. And we have to be careful with our signs. Anything that's on the left side of the mirror, we say is real, and so it's a positive number, so dO, dI, and F would be positive. If it's on the far side, then we'll call it negative. So for a convex mirror, where the focal point's on the far side and the center of curvature is on the far side, those numbers would be negative instead of positive. To get the magnification, which is the ratio of the height of the image to the height of the object, it's just minus dI over dO. If you get a negative value for M, that means that the image is inverted. And if you get a positive value for M, then the image is upside right. So like I said before, in general, a real image is going to be upside down, have a negative magnification, and a virtual one will have a positive magnification and be upside right. So for a convex mirror, the image is always virtual, upright, and smaller. That's like the passenger side mirror on your car. And when you put it into the equation, you always have to have that F as negative. For a concave mirror, the image can either be real or virtual. It can be upright or inverted, or larger or smaller, and that depends on the location of the object with respect to the focal point and the center of curvature. And for a concave mirror, F is always positive when you put it into the equation. So let's do a quick example calculation. So I've got an object 42 centimeters high, placed 2 meters in front of a convex mirror with a focal length of 0.5 meters, and they want us to find the location and size of the image, and is it upright or inverted. So I've got the height of the object, I've got the distance the object is away from the mirror, so that's dO. I've got the focal length, I've got F, and they want me to find the location of the image, dI, and the size of the image, HI. And they want to know, is it upright or inverted? Well, we can tell them right away. It's a convex mirror, so it's got to be a virtual upright image, but let's do our calculation. All right, so we expect that the image should be virtual, upright, and smaller. So we expect DI to be negative because virtual, and we expect M to be positive and less than 1. All right, so let's do our calculation. So we have 1 over dO plus 1 over dI equals 1 over F. So if I want to find dI, I'll subtract the 1 over dO term to the other side. So 1 over dI equals 1 over F minus 1 over dO. So dO is 2 meters, and F is half a meter, and I have to be careful and put in a negative sign. So it's minus 0.5 meters because it's a convex mirror. And that's the biggest mistake that people make. So if I put that in, 1 over dI is 1 over negative 0.5 minus 1 over 2, and I get minus 5 over 2. So dI is 1 over that. And so if I put that in my calculator, I get 0.4 meters. So remember, when you get to the end, always take 1 over to give you the final answer for DI. So DI is negative. So if it's negative, that means it's virtual. Okay, how about the magnification? Magnification is the height of the image over the height of the object. So I know the height of the object. And it's also equal to minus DI over DO. And I know DI now, and I know DO. So I can calculate my magnification using that second part of the equation. So minus DI, the negative of negative 0.4, which gives me plus 0.4, over 2. So my magnification is plus 0.2. So the magnification is positive, tells me that it's upside right. The magnification is 0.2, tells me that it's going to be 20% of the image is going to be 20% of the height of the object. So if I use M equals HI over HO, I can rearrange that to give me that the height of the image is the magnification times HO. So it's 0.2 times 42 centimeters, and the image is going to be only 8.4 centimeters tall. So what I want you to do today is I've given you here for a focal length of a mirror being 10 centimeters. I've given you all the possible cases that you could be asked to draw. So all these different object distances, you can see whether it's concave or convex. And so I ask you to draw each of these situations on a sheet of paper. Draw the special rays, draw where the image is located, and then mark on the table. You should be able to see there's a worksheet online that you can download and fill in if you like. Whether it's real or virtual, upright or inverted, larger or smaller, and then use the two equations at the bottom to calculate actual numbers for the image distance and the magnification. And if you can do all of these, then you can do any situation that I could give you on a test or on a homework assignment.